Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving into the fascinating world of PCBs, specifically the evolution and purpose of copper pores and ground planes. It's a deep dive, so buckle up.
I'm ready. So, the article starts by showing a stark contrast between older and newer PCBs. The difference is striking, isn't it? It's not just miniaturization. It's the massive use of copper pores in modern designs. What's the deal?
Exactly. The shift is dramatic. The article points out three main reasons. First, high-speed electronics benefit from improved signal integrity with copper pores. Think smartphones and modern computers. That speed demands it. Second, FCC regulations on unintentional radio emissions. Copper pores help reduce those emissions, saving manufacturers time and money on testing. And third, it's a bit of a fashion statement. Hobbyists often emulate industry trends, even if they don't fully understand the underlying reasons.
Interesting. So it's not always purely technical. But the core question remains, why do copper pores actually work? The article gets into some serious electromagnetism here, doesn't it?
Absolutely. It's all about inductance. The flow of electrons isn't just about particles bumping into each other. It's about electromagnetic fields. Materials like ferrite absorb energy from these fields, creating inductance. Think of it like a resistance for AC signals. A common mode choke, for example, uses this principle to filter out common mode noise.
Right, common mode chokes. I get that. But how does this relate to a copper pore on a PCB? It's not like there's a ferrite core there.
That's the clever part. Even without ferrite, any trace on a PCB has inductance, albeit much smaller. With a copper pore on the back layer, the return current path for a signal trace on the top layer is essentially mirrored. This creates a situation similar to a common mode choke, where magnetic fields cancel out, reducing impedance and improving signal integrity. It's a clever way to manage inductance without adding bulky components.
So the copper pore acts as a kind of distributed common mode choke? That's a really elegant explanation. But the article also mentions potential downsides, right? Like increased capacitance?
Precisely. While reducing inductance is beneficial, the copper pores also increase shunt capacitance across the entire PCB. This is generally fine for digital signals. But in analog circuits, that extra capacitance can be a real problem, potentially leading to instability. It's a trade-off you need to consider.
I see. So it's not a universal panacea. The article emphasizes that for many hobby projects, it's not strictly necessary. It's more of a convenience than an absolute requirement, unless you're dealing with high-speed interfaces.
Exactly. For ESP32s, Raspberry Pis, or 8-bit AVRs, adding copper pores is often just a matter of making life easier. But once you start working with MIPI DSI, USB 3.0, or other high-speed interfaces, understanding the implications of inductance and capacitance becomes crucial. It's all about context and understanding the trade-offs.
This has been a really insightful discussion. It's amazing how much is packed into something as seemingly simple as a copper pore on a PCB. Thanks for breaking it down.
My pleasure. And remember, listeners, always consider the context of your project. Don't just blindly follow trends. Understand the underlying principles. That's the key to good PCB design. Thanks for tuning in to Tech Bytes and News. Have a great day.
Bye-bye.